be used either it can be used in a mechanical APDL graphical environment in Ansys, or it can be used in Ansys mechanical workbench actually. So it can couple with the various different applications in Ansys like Design Explorer and Space Claim, which are the CAD modeling software in Ansys. And other than that, it can also couple with the Composite Prepost Maxwell for doing some composite analysis as well as the electromagnetic analysis. So mainly it can be coupled with a different material library in Ansys itself. There is one default engineering material library we called engineering data, and another library which is the Grant IMA, which is the very big data material library database where they have maintaining like more than 4,500 materials in that library. So it can couple with that kind of a libraries and it can perform the analysis. So, like this particular multi-scale SIM software is targeting different materials of composites, starting from fiber reinforced plastics, which is widely used in aerospace industries. It can and also in the filler dispersed plastics, which is mainly used in electronic industries. So and other than that, the materials like porous materials, like formed lattice structures, honeycomb materials. Other than that, it can also used for performing the polycrystalline metals, property prediction of polycrystalline metals, multi-phased metals, and punching metals. It is targeting different industries as such, like heavy industries, like aerospace industries, where they used composites almost like 50% of the material in aerospace. It is used in composites only. So apart from that, the composites are used in a different field in medical industries, like making artificial hip joints, artificial bones, using lattice structures and the porous mediums. And there are some components where the composites are used in MRI scan, MRI instruments also. And the energy industry is also it is targeting, and especially it is targeting the electrical and the magnetic in the electromagnetic industries like semiconductor packaging, where the semiconductor packaging is made by composed of FR4 sealing resins and solder bumps and circuits. So these are the industries it can target for material development. So apart from that, we using this software, we can perform different problems like creep problem in in electronic industries, in semiconductor industries. Where in semiconductor industries, it is composed of more than 4 elements like copper, epoxy resin, E4, FR4, and SR. So you can build this kind of a component, and you can perform the creep problems also, and plastic related problems and other problems less like frequency modal response problems and vibrational problems also it can target. So basically, the multi-scale simulation software is works on the principle called a homogenization theory. The homogenization theory is nothing but is a mathematical method to predict the effective property of the composite material itself. So it is basically it is an assumption like it will idealize the composite material as a homogeneous material with an effective set of properties. This is the basic theory of homogenization theory. So normally composites are made up of more than two or more materials like phases, for example, or layers, such as we call as binders or matrix or reinforcing fibers. So these multi-layers can be composed as a single as a homogeneous entity by using this homogenization theory. So it can calculate different effective properties of composites like starting from structural, thermal, as well as the electromagnetic. But here we are going mainly targeting the electromagnetic properties development. So basically, like, in order to develop the material properties, we need to characterize the characterize the microstructure of the material that I will be showing in the next slide. So normally, for an example, suppose if you want to perform some kind of an material property determination for a wind turbine blade, this wind turbine blade is composed of a microstructure with epoxy under the this kind of a fibers. This is an SEM image, and this SEM image can be converted into a 3D model, CAD modeling CAD modeling images or models like this actually. So where using this image, we have extracted some geometrical parameters of the fiber dia and the volume fractions of the fibers and the volume fractions of the matrix, and we have converted using that available information into a 3D model like this. So this 3D model are subjected into a virtual material testing where you can get all the material properties. The property what we have gathered from the multiscale sim can be extrapolated, or we can convert it into an equivalent material property for our macro scale analysis. So firstly, the micro scale analysis, that is virtual material testing using homogenization analysis, will be performing. The whatever the material property we are taking from the multiscale sim, it will be converted or translated into the mesoscale level as well as the macro scale level for our bigger or macro level analysis. So in the some of the examples I will be showing in later slides. So basically, like this is the working setup or the operational setup for a multi-scale sim. For example, if you want to perform a virtual material testing for a one case, so for example, so this is the unit cell or this is the RV model we are going to uh, exam is available in the multi-scale sim. So there are a lot of templates are available in the microstructure templates are available in the multi-scale sim. Nearly 16 types of microstructure templates. The very few of them I have shown here, displayed here. So then after having the microstructural model, so it will subjected into some kind of a virtual material testing in order to extract the material property. So those material property extractions can be processed or data processed and it can perform the parametric studies and the design of experiment. So by this way, by performing all those things, we can come up with a proper material or the proper design of the composites can be done by using this software. So first, the first thing, like in order to perform this operation, whatever I have explained in the previous slide. So in order to perform one particular virtual material testing simulation, we need two input parameters are main, like the observed micrographs, which is taken from the either SEM or from the optical microscope. From the observed microstructure, we can extract different geometrical parameters, like starting from the width and the width, length, and the height of the microstructural model, and the filler in which uh, the filler volume fractions or the matrix volume fractions, the different things we can extract it actually. So this microstructure is used for extracting the geometrical parameter and constructing a 3D microstructure template. Apart from that, the material property of the each part. For example, if you are going to analyze if you are going to perform a virtual material testing for this particular composite, which is the filler dispersed one, the filler property we need to know as well as the matrix material property we need to know. So this is the input parameter we need. So totally two input parameters, that is the microstructural model. In order to construct a microstructural model, we need to have some kind of a geometrical parameters, all the geometrical parameters, and then the material properties of each component available in the composites we need to know. So once we have put all the input parameters, we can perform the microstructural virtual material testing in order to get a stress strain curve or electromagnetic properties as such. So this is the environment, graphical environment in which in ANSYS, where you can see the lot of microstructural templates and uh, and some kind of geometrical parameters where you can vary the geometrical parameter in order to construct the microstructural models. And this is the window where you can perform different analysis So I will be showing in the next slides, next few slides. So these are the available microstructure templates of for the composites, starting from a single dispersed one, multi-dispersed filler, the unidirected one, and the polycrystallines, the short fibers, elliptical fillers, honeycomb structures. So nearly there are a lot of 16 microstructural templates are available here. So this is the representative microstructure available in the multi-scale sim as well as in the space climb. So either you can for modeling this microstructural template, either you can use space climb or design and modeler. So these are different CAD modeling software in ANSYS. So apart from that, we can also define, for example, this is an SEM image, what we have gathered from the SEM. So where we can derive some informations related to geometry, the filler dia, the the distribution type of the fillers, we can see here. So using this information, we can construct the model, and we can there are some options we can say that the fillers are distributed randomly, or it is distributed in aggregated manner, or it can be distributed in biased manner. So these are the different distribution types. We can there are different available options in multi-scale sim. So apart from that, the fibers also we can perform. Mm, the orientations of the fibers we can control, and the volume fractions of the fibers as well as for the fillers can be controlled using using available data. So the different analysis can be performed using multi-scale sim. So starting from structural, thermal, fluid, and electromagnetic. So our aim and our interest, we will be seeing in this session only on the electromagnetic, the permeability or permittivity and electrical conductivity properties only. So as I told you in the previous slide, the multi-scale SIM has can be coupled with the different applications available in ANSYS, starting from design and modeler and space climb. So this is the CAD modeling software interfaces available. So design and modeler, and then ANSYS application, ANSYS mechanical workbench or ANSYS APDL, and then it can come whatever the material property what you have developed in multi-scale sim can be inputted so it can be exported to the Maxwell or the LS data, which is the different ANSYS applications available for performing the electromagnetic analysis. Also, some the laminated structures and the fiber orientation after drafting using ANSYS composite pre-post can be also performed, can be coupled, and it can perform whatever the material property you have gathered. So apart from that, you can couple with ANSYS Grante MI, which is the material library available here. So So you can see here there are the different analysis can be performed uh, in a PCB board actually. So we can perform the distribution of temperature using different CA tool for analysis like ANSYS Fluent, ANSYS Ice Pack, ANSYS SIP. Um, but whatever uh, the analysis you are going to perform, you need material property. That is very important criteria for performing the any analysis. For example, if you want to see the distribution of the temperature, you need the properties like thermal conductivity and the electrical conductivity in the PCB. So you can and uh, and other than that, the mismatched material constants can also be performed in so this kind of using ANSYS mechanical environment, and some non-homogeneous materials like in wiring distributions uh, where you can see some kind of fiber reinforced plastics and some filler dispersed plastics. so material, the composite materials will be seen in this PCB board. So you can use the multiscale sim for this kind of analysis also. So normally this wrappage in a PCB board, it is composed of like different materials, starting from the filler dispersed the filler dispersed plastic material and the solder bump. You can see the solders, and there are some addues which joining the semicon and the IC. Uh, the different electronic segments into the PC into the board into the PC board can be constructed. It's of composites only. So these are the different materials. These are the different composite materials available in the PC board. So you can use the material. You can use multiscale sim, to extract the material electromagnetic material property for this materials. So, for example, if you want to analyze a fatigue analysis for the semiconductor packages, which is composed of, as I told you, it is composed of different uh, layers, starting from the heat spreader, TIM, and the silicon dies, solder bumps, underfill, the copper wirings, FR4 substrate, and the chip parts. So these are the different these are the different composites which is placed in the semiconductor packages. So if you want to analyze the fatigue property, you need certain properties. So these properties can be extracted using multiscale sim, and the equivalent material, the creep properties are performed using multiscale sim. You can see here we have performed the creep equivalent. I have compared the equivalent creep strain versus strain with the homogenized model, that is the multiscale sim model, as well as some detailed model and the simplified model. There is, you can see the comparison between all the models. It shows a very good agreement between all the models. So this is how we can perform on the creep property. The creep equivalent creep strains can be performed. So apart from that, the if you want to analyze if you some the Young's modulus properties of the semiconductors, you can perform it here. Like this particular semiconductor, the sealing resin is composed of a silicon carbide filler plus epoxy resins, which is having a spherically filler distributed composites actually. So using the homogenization techniques, the Young's modulus, the shear modulus, and the different properties as material properties can be extracted, and we have compared with the experiment also, and we have seen that there is a very good agreement between the analysis as well as the experiment results, as a functions of the filler volume fractions. So similarly, there is some adduce conductive adduce. So for that, we have the silver fillers in matrix are used, which having a high conductivity. So in order to do that, to have a high conductivity silver filler, we have extracted the material property of the epoxy resin plus silver filler, and we have created the 3D model, the microstructural model, using image based techniques. That is X-ray CT scan. So we have analyzed the different layers of the microstructure, like for every 300 microns we have scanned, and we have taken out the 2D images. Those 2D images are assembled together using the simple ware software in order to construct the 3D, the total 3D model. So using this model, we have performed the homogenization analysis in order to extract the material properties uh, starting from true stress and the true strain, the thermal conductivity, and the electromagnetic properties as well. So normally in semiconductor industries or in electromagnetic property determination, the filler dispersed composite packing are used. So the main important thing in the filler dispersed one, like we have to set or say what kind of distribution it has, and the particles or the fillers are distributed. We can say that it can be uniformly distributed. If it is uniformly distributed, the packing rate will be like 63%. But if there is a Gaussian distribution, then there is a 66 percentage of the packing rate will be there. And if it is biased one, it is a 69 package, 69 percentage. So according to the packages in the available in the composites, you can modify the microstructural model and perform your virtual material testing. So here there is one example where we can see how the filler sizes are affecting the electrical conductivity. You can see here, like uh, you see the electrical conductivity, which is varying as a functions of the volume fractions of the filler. So in the red plot, which says that the filler size is around 1 micron, whereas the blue one, which says there is a filler size having both 1 micron as well as the 0.5 micron. So by having just 0.5 microns of filler size, there is the drastic reduction in the the electrical conductivity is seen after like after 45% of the volume fraction. You can see there is a drastic reduction in the electrical conductivity by varying the volume fractions of the filler. So these are the properties we can compare, and we can do the different kind of the parametric studies in order to design the composites. So and the another one thing is like another one case is like predicting the electrical conduction. So this is the microstructure. This particular composite is made by the alumina filler as well as the carbon nanotubes. Our main aim is to calculate to evaluate the electrical conductivity of this particular microstructure template. So what are the geometrical informations what we have gathered from the microstructures are used in order to create the micro model like this kind of thing. And these are the SEM images we have used for having the geometrical parameter for constructing the micro model. So once the micro model is created, the homogenization analysis using the multiscale SIM is performed. So then the equivalent the thermal or electric conductivity properties can be extracted as a functions of the carbon nanotubes. You can see we have compared both the experiment as well as the analytical uh, uh, and as well as the simulation one, and we have seen that there is a good agreement between the experiment as well as the simulation part. See here, this is how this the multiscale sim was validated for the electrical conductivity in the presence of the carbon nanotubes pillars. So until now, so this is the basic the overview of the multiscale sim. So if you have any doubt regarding the multiscale sim, you can ask now. Next, I will be demonstrating about some few examples using multiscale sim. So do you have any doubt? Hello. Yeah. Okay. Then we can go to the next one, like some operational demands, some examples. So first electromagnetic analysis, firstly I will be performing. So for example, uh, the one particular electromagnet the electronic part is composed of the two layers with having a relatively different permeability, like the left layer which contains the relative permeability of 1, uh, whereas in the right layer which contains the relative permeability of 1000. So this is the information, the geometrical information is available. So available here. So these are the element size I will be using. Uh, So we can perform one analysis. For example, in order to analyze, so we need to start the multiscale sim. So by going into the Cybernet tool, which is if you have installed the multiscale sim, as I told, the Cybernet software, which is they are the responsible for maintaining the multiscale sim. So we need to launch this multiscale sim launcher. So there where you can see this kind of a small graphical window. Now we can go into the mechanical APDL model, linear mechanical APDL model in order to perform the electromagnetic analysis. So we can run. So this is the one, and we have to set our the working directory as well as the name, like whatever the name if you want, you can set it. So you can run it. So this is the APDL window, the mechanical APDL window. So so in order to construct this particular micro and then this particular microstructure template, we can I'll be constructing this one. Like for that, we need to go into the preprocessor. In the preprocessor, first before constructing the model, we need to say what kind of the element type it is. The element type is a scalar brick. So we have to define the element type. Then after we have to define we have to define the different geometrical parameters. Then we have to define the material constants. So these are the things I will be doing now. So once like element type, if you go into the element type, you just see here add. So it is basically a finite element analysis. So we need to set an element type. Going into as we are going to analyze the magnetic analysis, we have to go into the element type of a magnetic vector and scalar. So we can use the scalar, which is very linear. The scalar brick 96 we can use. So then we can click OK and close it. So once you have set the element type for our analysis, then go into the material property. What we need to, so going into the material model. So we have to define, you see in the slide, like the relative permeability of one material, which is 1, and another material, it is 1000. So this is the material constants we have to input. So the relative permeability constant 1 for one material and another material we need to create. So going into the material tab in the window and create a new model, and model ID is 2. So by clicking OK, material model now number 2 is created, and we have to define the relative permeability constant for this material 2. So here the another material which has the relative permeability, it is 1000. So we can say it is 1000. So this is how we have defined the material property of 2 layers of the composites. So once we done with this one, so next one we need to model actually. So the model the 2 layers, that is the model the 2 layers. This is the dimension what we have, like 0.1 e power minus 3 and 0.1 e power 7, the same thickness, and almost the same, like 10 times larger length as well as the width. So we need to create one. So create volume, and this is kind of a block, like a rectangular blocks. So we can say we have to create a volume with a block by dimension. by dimension. So we can specify the different coordinates x and y. So x0, as it is, we can see here it is e 0.1 e power minus 3. So 0.1 e power minus 3, 0, 1 e power minus 3. This is the width in y direction, and height, no, 1 e power minus 3. So, one material has been created. Okay, in the left layer, which was created now. So next, the second layer has to be created. So again, click by dimension. So this is the another layer which will be starting uh, from this coordinate. So the right layer also created. So thereby we have created the two models, which is the volume models. You can see like will rotate. You can see this is the two layers which has been created using our options available. So once we created the model, the next procedure we have to mesh the model. So the meshing has to be performed. So then we have performed the element type, then material property we have to define. We have defined, and a model has been created. Next, meshing. For meshing, we have to go to the mesh tool. Mesh tool, and we are going to mesh by volumes. So check out the volume set. Okay, and the number one material we have to choose, like pick this material. Okay, and we have to define the material property. Like we can say this particular layer, which is composed of material number one with the solid element type, which is a solid 96 element type. What we have, other properties are default. So okay, then again set, we have to define for next layer. So click this one and click OK. So two and click OK. So this is how we can set all the things. Now we have to mesh. Like our aim is to mesh the volume using hexa mesh element with mapped options. So we can check out the hexa and mapped options and click mesh. Click mesh and pick all. It got meshed actually. This is how it is meshed. So we can close the window of a meshing. So now, if you want to see the different materials, you can choose a material number by color and apply. So you can see here, there are two materials. One is with the left layer with a relative permeability of 1, and another one is with a relative permeability of 1,000. So this is how it we have modeled and we have meshed. So now this model it is ready for our homogenization analysis. Normally, as I said, multiscale.SIM is an extension available in Ansys. You can see here, if you have installed multiscale.SIM uh, extension, you can see the multiscale.SIM. It will be appeared here as a command prompt. There, in the multiscale.SIM, there are different options are available. Like as I said, this basically the material property, whatever the material property for composites we are going to predict, it is based on the homogenization analysis. So for the homogenization analysis, there is one tab. Uh, so in that there are different things like micro models, the default micro models, the material property meshing and homogenization analysis are available. And apart from that homogenization model, macro analysis also we can perform, and homogenization and localization analysis also perform. There are different options we have. So here we have set all the um, the model was ready for our homogenization analysis. So you can go to the multi-scale sim homogenization analysis. In a homogenization, go again homogenization, evaluate homogenization property, linear analysis, and solve. In solve, once you click the solve, you can see this window like this window will be appeared where you can perform a different analysis like elastic, thermal, sweepage, current, electric, and magnetic. Now we are going to perform in the magnetic relative permeability property. So we can check out the magnetic one. Before that, we have to name this. So we can name as magnetic homogenization analysis one. Like that, we can name and we can say OK. So and then we have to set the MXS unit. So by setting OK, it is ready for run. So this is how it is run, and our solution will be the total the relative permeability of the composite is our aim to predict. And this was predicted, and I have already done this, and I have predicted, and I have put it in the slide. So you can see here. Uh, so this is the relative permeability of the after homogenization analysis. Once you got this particular the material property, the relative permeability of the permeability. Sorry, here I have mentioned permeability, permittivity. No, not it is a permeability. So these are the permeability what we have gathered for all the directions. So what are it can be put for our macro analysis. Actually, uh, the layer what we have taken is this is the layer. We have taken only the two layers, and we have run our homogenization analysis. This is the magnetic shield of the laminated structures. This is the microscale layer, which is used in the magnetic field, which where you can see the existing oil under the. This is the proper ma, uh, macro model, and in order to have the material property, we have taken out a RV, that is a representative volume element model, microstructural model we have taken, and that in that we have taken only the two layers. Once we have applied the material property of the two layers, we will be getting the material property of the total composites itself. This is the material property of the composites. And this material property can be used for our macro model. So this is the macro scale model. For our aim to perform the macro model is to have the distribution of the magnetic flux density. So in order to perform the magnetic flux density, we need to know the relative permeability and the permittivity. So these are the informations can be gathered from the multiscale sim. So you can see here. So, the distribution. So once the macro model consumes a lot of time. So here I cannot show the total macro model analysis. So after performing the macro model analysis, the distribution of the magnetic flux density can be seen here. So this is the result of the distribution of the magnetic density. So this is the one example for relative permeability. Then we can go to the another example for electromagnetic analysis too. In this case, you can see here. Here we need to perform electrical homogenization where the relative permeability here the permittivity we have to see the of a composite which consists of ferroelectrics and void. There is a void inside the uh, ferroelectric in the in this material. So you can also perform analysis, the microstructural analysis with the void as well as with some kind of inclusions also. So similarly, the whatever the procedure what we have performed for predicting the relative permeability using APDL, the same thing we have to perform. Just to change, we have to create the electric the micro model, and we have to define the relative permeability. permittivity. So once we have once we have constructed and extracted the model, so this is the material property. That is the relative permittivity property after the homogenization the analysis in all the directions, in x direction, y direction, and z direction. So this is the macro analysis model actually. So what are the input? What are the material property you have gathered from the micro model? You can export to the macro model for the macro scale analysis. This is the macro scale analysis. So this is where the ferro electric the homogenized ferroelectric is located, where you can apply the material property gathered from the multiscale sim. So you can apply that material property and the different uh, the post processing parameters like electric potentials can be extracted, and it has been displayed is here, and electric field intensity is also displayed here actually. So this is how the electric as well as the electromagnetic properties that can be performed. You see. So going to the last example, this is the electromagnetic analysis for three, the third analysis. So our aim here is to investigate the dielectric characteristics of the composite laminated material actually. So the for a composite material, so the main aim is to in order to optimize the performance of an antenna as we know that the electric property, dielectric property of the composite material plays a very crucial role in transmission and the reception of the microwave signals by using antenna. So this dielectric property of the composite material is very important. So we have to design a proper dielectric material so that it can be used in the antenna. Here we have to made the different materials which can be used in the antennas need to be collected. So I'll be showing in the next slide. So the property what we need to take out, it has to be with a very low dielectric constant and lower loss, tangent loss actually for this application. So this is the aim. So we have to collect the materials, the different materials with such kind of property. So we have collected for resin, and we have collected the polyester resin with dielectric constants of the 4, and epoxy resin with dielectric constant of 3.3, and polyether resins with the 2.7, and phenolic resin. So these are the resins, different resins with the different dielectric constants. And fibers, there are different fibers like e-glass fibers, carbon fiber, and S2 glass fibers, so boron fiber, ceramic fiber. So these are fibers with the different the dielectric constants. So our aim is to have the lower dielectric constants. So we need to put some kind of a permutation and combinations method in order to create develop a material for the composites. So we have performed that for so the model microstructure model we are going to use is this one. This is the woven one microstructure which is available in the multi-scale sim itself. So this is the dimension we have used, and with the matrix volume fraction, that is epoxy resin volume fraction is 50%. Like resin volume fraction is 50%, and fiber volume fraction is 50%. So 50-50. So this is how it constructed. After doing some kind of permutation and combination, we have selected only three resins and three fibers. So the dielectric constants for these resins are very suitable at a different frequency level, the electromagnetic frequency levels. So you can see, and we have chosen the urethra as a slate with the dielectric constant of 2.7 in different frequency, and polyester and epoxy. And similarly, we have choose the fibers like cost and S2 glass and E glasses. So with the dielectric constants. So we we perform the dielectric constant. The result is after performing a and after performing the homogenization analysis for these three combinations, like urethra coast with the different composites, because we have seen that by having 35% of the fiber, this particular composite, that is, urethra or slate composites having a very low dielectric constant, that is 3.19 and 3.27. So this is very having very low dielectric constant. So this particular the combinations of a composite plays it can place a very important it can place and it can be used for our antenna constructions other than the polyurethra S2 glasses and epoxy glasses. So in a summary, like we can say that in order to analyze the electromagnetic analysis, or in order to construct the material for the composites with having a electromagnetic properties, that plays an important role. We have to be very careful while choosing the different uh, fibers as well as the matrix components in the composites. So, and also the diameters of the fiber as well as the fractions of the fiber, volume fractions of the fiber, and the pitch in which the fibers, as well as the void fractions, which is distributed in the fiber, plays a very important role, very crucial role in determining the electromagnetic properties. So this is the summary for from our analysis. So any doubt so that I can show some kind of a microstructure template apart from our topic. Do you have any doubt, please?
Sir, kindly explain the third example that you designed that model.
This one. Yeah,
Only its geometry. Yes, sir. How can it design on the CAD or something?
in CAD. Okay. In CAD, we can construct wait. Okay, so multi-scale sim launcher, like going into here in Workbench, run. So it is an extension, as I told, the multi-scale sim. So this is previously I have shown the mechanical APDL environment. Here I am showing you the Workbench environment. Here there is a multi-scale. You can choose this one and close it. You can see here there are different geometries, different templates. You can see. And the geometry, the microstructure template, what I have used in the third section is this one, the high cross. So which is readily available, which is in the multi-scale sim template itself. So go to edit geometry in space claim under design modeler. These are two CAD modeling software available in Ansys itself. So go to edit geometry in space claim. So it is opening. The space claim is opening. It takes a little bit time. So Okay. So this is how I have created so this particular template available in the software itself, the Multiscale.SIM software itself. So I didn't put more effort in creating this particular thing. In this space claim, you can there are different options in order to adjust the volume fraction, the diameter of the fiber, the thickness of the thickness of the fiber, and the matrix. These are the parameters, geometrical parameters where you can work on actually. Here you just create like say like 50 something, and you can run the script. So it automatically
Sir, one more question that the both
yeah.
bodies treating as an individual, or how can it connect with each other? Like one is matrix and another is fiber. So how does it
Yeah,
interact with each other?
and there is a contact we have to define. So by defining the contact, it can interact each other in Ansys. You can see one example. Maybe I will show one example. So here I have opened one example of this particular model. That particular model what I have shown before. This is completely structural analysis. You see, there is a connection. It automatically takes connections, like generate automatic connections. But with having this kind of mesh, it there will be connection between the two meshes. You see here, there will be connectivity between the mesh between of the two components. So thereby it can interact.
Okay, sir. Thank you.
Yeah. So, so any other questions? Hello.
No, sir. Thank you.
Okay. This is this is for like I can one model, and there are different microstructure templates available. Like you can see just now I have shown shown for high cross. There are some fully dispersed one, the multi dispersed one, which is mainly used in the electronic industries. So you can see this is the multi dispersed one. The multi dispersed one, we can edit geometry in the space claim. So you can go to edit geometry in space claim. So you see here. So this is how the microstructural model looks like. Okay. So by playing with the average radius, the radius, the maximum, you can see here, like you can play with the radius, minimum radius for constructing, and you can go and you can run the to create a. Yeah, so the total thing is it has been changed. The distributions of the particle, the distribution has been changed. So similarly, you can also say whether it is a biased one or it is a randomly distribution by defining the distribution type, whether it is one or two or three. The one is like a uniform one, the random one or three, and the biased one. So there are different options available here actually. So if I go one example for the thermal conductivity problem. So in order to perform the homogenization analysis for having the thermal conductivity of the any material, so these are the procedure we have to follow. Firstly, we have to define the engineering material property of the each part in the composites itself. So for example, if I go inside the engineering data, so just by double click. Uh, uh, Here you can define like a different material. Like here I have specify aluminum alloy. So you can specify any other material in composites. Like you can say like aluminum alloy as a matrix, and you can put some other inclusions or the voids in the material, and you can define the thermal conductivity of the particular material. So here for the aluminum alloy, the isotopic thermal conductivity I have defined. This is the graph I have defined here. So this is how you can define the material property in the workbench, in the mechanical workbench environment. After that, as usual, you have to create the geometry. You can use there are two CAD models available. It is a design modeler CAD model and the space climb. And there are different geometries, ready-made geometries available. Also, there are 16 geometries are available. Maybe I can go to the design modeler and I can show the different models. So you see here. This is a honeycomb structure actually. So you can see here the multi-scale extension where the blue one everything is a microstructural model. Almost 16 is there. The single fiber, multi-particle, the multi-ellipse one, the unidirected one, the random unidirected, the cross wave, weave, hard fiber, blade, and the woven, like different things are there, like polycrystalline, even the honeycomb structures, the lattice structures, and the fibers pure mixing. So this is like 16 types are available. The ready-made geometries are available. Even if you want to create your own geometry and if you want to import into the analysis, you can perform that also. If you have worked only in the solid works and some other CAD modeling tool, you can import as a step file into the space climb, and you can convert that into SC doc format, which ANSYS supports. You can convert that and you can use it for the analysis. So it is compatible for any geometry, any CAD modeling geometries, and any CAD modeling softwares also. So once you have created the geometry as well as once you have specified the engineering material data, the final thing you have to perform the analysis on the homogenization analysis to predict the material property for the model what you have construct for the composite model what you have construct. So here I have already done this model. So I just showing how I have performed this one. So this is the geometry. This is the honeycomb structure, and the material I have used is aluminum alloy. Uh, for an example, I am using the aluminum one. Whatever the material or whatever the composites, if you want, you can use it, no problem. And this is the meshing what I have defined and I have constructed, which is totally hexa mesh, very well connected. And you don't want to and you can, this is the homogenization settings in Ansys mechanical model. You can see the multiscale extension. It looks like here the multiscale sim linear one, where you can perform all the linear kind of things, starting from the elastic modulus, the elastic modulus, the Poisson ratio, the thermal conductivity, and the thermal expansion, the specific heat, and electric uh, dielectric constants, electromagnetic properties, the different properties you can perform using linear itself. If you are going to the non-linear one, you can perform some kind of a elastoplastic non-linear behavior of the material. And this is totally related to structural analysis. This non-linear property support by multiscale sim. So this is how you can perform the non-linear analysis also. So if you want to do this simple numerical material testing in tensile material testing, you can use this option. That is numerical material testing, where you can perform the tensile test in X direction or Y direction or Z direction, and even for the pure sharing and pure sharing in X, Y, Y, Z, and ZX direction, in different directions you can perform. So this is how you can perform it just by saying like we are going to perform the homogenization analysis. You don't want to that is more sufficient without giving any boundary conditions for your analysis. It automatically takes or it automatically fix the boundary conditions by itself. This software, this multi-scale sim software. So once you done with that the homogeneity settings, you can run for the solution, solve for the solution, and you will get the different material properties like thermal conductivity, density, specific heat for the total composites available actually. So so once you run, you can save this. You can import to the engineering data library available in Ansys itself, and you can use that this input this material property data for your macro scale or for your further analysis. For different analysis, you can use it. So this is how it works. This is how for thermal field. Similarly, for if you are going to work in a static structural one, there is a static structural properties also. If you are going for the thermal electric, there is a thermal electric where you can perform whatever the properties where I have what I have shown. No, the relative permittivity, those things also you can perform here. So these are the three modules where you can perform this. Hello. So any doubt? Hello. Yeah, uh, yeah, like